So today we're going to be talking about references, but before that, we need to talk about variables. So variables, things that store values in our code. And as of yesterday, we've mostly only been talking about primitive types. So these are ints, doubles, chars, booleans. These are certain properties that we'll get into. Today, we're going to be talking about the second type of variable that we'll cover in this class. The more interesting type, I believe, which are reference types. And these come in two different flavors, or two different sub-flavors, I guess you could say. You have the immutable types, and then the mutable types, which was something we went over on Tuesday when we talked about natural number, as natural number is an example of a mutable reference type. An example of an immutable reference type would be something like XML tree. I will say the distinction between these two types of variables, primitive and reference type, as somebody who has now graded the final and then midterm 2, is the biggest thing that people miss, is the distinction between these two variables and how they work in memory. So if you can get that down, I will say you will have a much better time on midterm 2 and the final, because people miss this a lot. Okay. What do they miss? Well, the fact that primitive type or primitive types, their values are stored directly in memory. So when you declare an integer, or you declare a double, char, or a boolean, the picture that we've shown is you have a box with the variable name, and then the value is contained right there in memory. So if you were to look inside, if you were to get very small, like Osmosis Jones, and go inside your computer, you would see that wherever X is stored will be the actual value of your variable. That's a primitive type. This is in contrast to reference types, space, where the values, or not the values, references to the values are stored in memory. So instead of the actual, lo and behold, value that you're trying to store, you store a reference to where the value actually is. References to the values are stored. So instead of, say, a 4 being there, if you have a reference type variable, you will instead, say, have 43. In this case, 43 is referring to another spot in memory, say, spot 43, 42, 41, 44. Where the value is stored, say 4. It's similar to a treasure map of sorts that you give Java when you're trying to use reference types. The actual value is not stored there. The location of the value is stored there. Yeah, that is the precursor for today. Questions on that so far? We'll get into it. We'll get a lot of practice with it. Okay, so Java types are divided into two different categories. The built-in types are called primitive types, includes Boolean, char, int, and double, the big 4. And then all other types are called reference types or class types. So we've actually been using a lot of them before. String, XML tree, simple reader, simple writer, and natural number. And then those are split into two different types, which are immutable, meaning they cannot be changed once they've been defined, and mutable types, which means that the value that is stored within them is allowed to change throughout the course of your program. There's no limit on the number of other user-defined types that can be developed. So all of the OSU CSE components are user-defined types that were developed, not included in the base version of Java. This is why if you ever go out into the real world, don't ask somebody what a simple writer or a simple reader is, because it's a custom thing only to OSU CSE. So if they did not go through the program, they will get confused. Yes?
Why do we do that then?
Why do we do that? The reason for it gets explained a lot more in software 2, but essentially, yeah, I hate to say it, but yeah, you have to wait till software 2. Software 2 is way more interesting in the sense that you learn why we do a lot of the stuff, but the reason we do it is because the way that you implement things, so think back to our class diagram, and then you have something that extends it. Given a contract or a interface, the ways in which you can implement that interface are both many and interesting. So there's a lot of different ways that you could go about implementing an interface. And some of them are interesting, and you do a lot of interesting implementations of interfaces in software too. So they want you to learn that eventually, but for now, we use our own custom components just because, trust me.
Okay.
But yeah. Okay, here's that exact chart that I just showed, which is primitive types plus 4 others, and then reference types. So you have your immutable types over here, and then your mutable types over here. Primitive type is a variable of primitive, or primitive variable is a variable of primitive type. Term is used sparingly in practice and is here for parsimony to distinguish a variable of a primitive type from a reference variable. Okay. The big difference here is that an int variable is of type primitive int, and a string reference type is of type string reference. Reference variable is fundamentally different from a primitive variable in ways that can dramatically impact how you reason about programming behavior. So beware. And that's what we'll get into. The big thing that people mess up is how you reason about reference types. So here is, again, this image that I've drawn right here, which is when you're using primitive types, those values are stored directly in memory at the spot of, or at the place of storage. So if you have a variable b, that value true, question? Oh, okay. That value is stored directly where b is stored. This is in contrast to reference types, where instead of the actual value, you will have a pointer which points to another location in memory. You'll notice that strings are actually not a primitive type, they are a reference type. And the reason that this is done is because strings can be very, very long in nature. And so we reason about them as if they were a reference type. Keep that in mind. People often think that strings are primitive types. They are reference types. Okay, so this is a string variable s whose value is go. This is how we have been drawing strings in the past. However, this is not the full picture. The full picture is this, which it's essentially you have a reference type, which are always represented by equilateral triangles. And that variable stores what's known as a pointer to the actual location of the variable. So in this case, the string go. What Java does when you say want to print out a string or use a string is it will dive deep into memory. It will look for where the reference is pointing and then follow that treasure map to the actual value. So Java does all this for you, which is very nice. Other languages do not, but Java has this in store for you. Okay. String variable s value is a reference to an object whose value is go. Remember, when we're talking about reference types, every instance of a reference type is known as an object, and objects are always represented with equilateral triangles. So natural number, simple writer, simple reader are all objects of type of a certain class type, which is implemented via an interface. This diagram, which you will probably be seeing in your nightmares for years to come. And then this is the reference s. Okay, good so far? And that is the object s, or sorry, the object s points to or refers to the string go. The mathematical string go.
Question.
Yeah.
It says references to the values are stored in memory.
Oh, did I forget an E? Yeah. Oh, I just drew it very badly.
All right, I just want to make sure I got that
Yeah.
in my notes correctly.
Yep, are stored in memory. Okay. Reference variable like s may be considered to have either of two values. So you can either be talking about the reference value of s or the memory address. The more important one is probably the object value, which is the second one, which is the actual thing that you're trying to store. So if we have our string s, you could technically say that this has two different values. You have the reference value or the memory address. This is the location where the actual object value is stored in memory. So your reference value. This is, say, I'm abstracting here, it's probably some large number, but it's 43 in this case. So we're saying that the actual value for our reference value s is stored at memory location 43. And then at 43, it's stored the object value or what we actually care about. A good way to, or how most people or some people might discover the difference between the reference value and the object value is, say you wanted to print an array. If you have ever tried to print an array by just out.println and then passing in an array, you'll get some weird like array like 0x4, 3, 2, and so forth. That's the reference value. That's where the array is stored in memory. It's not the actual object values of the array. In order to get those, you have to index. So by doing a sub 1 or a sub 2. And what that will do is it will go to the memory location and extract the object value, which is what we actually care about. Cool. Okay, think of the reference value as simply an ID or a serial number of some place in memory. I like to think of it as a treasure map because I like to think there's a little guy who goes in and grabs my reference values and goes on an epic journey to find the actual object value. And here's the real picture, or an abstracted version of the real picture. You have your variables, some of which are primitive types. So we've got like a bool, we've got a car, we've got an int, we've got a double, the whole team's here. These are actually stored directly in variable memory. However, we then have a reference value in which the actual value of what we're storing, the string go, is not stored with the other variables. Instead, a reference to where it is stored in object memory is stored at the actual value. So in this case, this would be like 22. So if you just print out, well, for strings, Java will automatically print out the object value. But for things like arrays, that's why when you print out an array, you get that weird long number because it's the reference location of the variable and not the actual object value, which is what you care about. Right. This part of memory holds values of primitive variables, remember, stored directly in the variable memory, and then reference values of reference variables. So mappings to where the actual objects are stored. And then this part holds object values of reference variables. And that's the big difference. But the implications are both severe and confusing. We'll get into those. Okay, each object in memory has a unique memory address or ID, e.g., this string go has 22. So at 22 is stored the string go. Really hammering it home. And then these numbers are the IDs of the objects. So if you had another string that was stored, say, at object location 24, it would point towards that. The reference value of a reference variable is the memory address or ID of the object of which it refers to. Again, pointing towards. So in this situation, it is indistinguishable in one program. Wait, what is it saying? It's immaterial. So in this situation, yeah. So the actual memory location doesn't matter. We don't care about it. Only in Java, though. In C and C++, you can actually do arithmetic with memory locations, which is confusing, but also very powerful. You'll get into in Foundations 1 why arrays are so cool is because you can immediately grab a location or immediately grab a value from wherever it is stored in an array in constant time, which is like epic in computer science terms. To everybody else, not so much. But the reason that I can do that is because this reference location is pointing towards the start of the array. So if we have an array of integers and we know how much memory an integer takes, what we can simply do is say, hey, go, let's say it's 8 bits, go 8 bits from the start of this, and you can immediately know where the integer is. But that's a systems 1 and systems 2 problem. For Java, you don't have to worry about it, which is nice. Cool. So we can simplify if we wanted to. We could draw pictures instead of actually just using numbers, like good business majors. Be abstracted as different shapes. All reference variables use an equilateral triangle. You will see many equilateral triangles throughout this course. You will see them in your nightmares. Okay, variables in the program are somewhere in this part of memory. Objects in the program are somewhere in this part of memory. We don't usually or typically care about where it is stored. We just want to know that it is stored. We want to know that primitive types are stored in variable types or in the variable part of memory. And we want to know that reference types, the object values, are stored in object memory. And then the references to those objects are stored in the variable memory. Okay. And then this is, I guess, the aha moment, which is that you have the reference which points to the object value. And this is the case for every reference type that we have. So if you have a natural number, called foo. It is a reference to a natural number, 42. If you have another one called foo2, we'll say this is a simple reader that points to some object location of a simple reader. Now, a simple reader doesn't have a value per se, so it's not that important to print out. I don't know what would happen if you printed out if you out.println a simple writer, what would happen? It would be bad either way, so don't do it. Okay. So we can finally even abstract apart the idea that they are stored in two different parts of memory, and then just know that if you have an equilateral triangle, which is pointing to something, that is a reference type. And if you have a value that is directly under a square or a trapezoid or a circle, that is a primitive type. How are we doing so far on this concept? Cool. Okay. We never care about writing the reference value of a reference variable as a particular numerical value. So we will never say, oh, this string S is 22, which is its reference value. Again, we don't care. We know that it's stored somewhere. We know that it's pointing towards some location in memory. We don't care about the actual value. What we really care about is the object value, the string go, the natural number 42, the simple writer. So if you see something like S equals go in a tracing table or a contract, it means that the object value of S is the mathematical value go. We're not saying that S is stored at reference location go in memory, because that would be pedantic, confusing. However, we might want to remind ourselves that it is a reference. So in tracing tables, if you are working with reference types, instead of having an equal sign, you will have an arrow. So instead of saying S is equal to go, you will say S points towards go. Slight distinction, but is an important one. Why would we do this? Well, that is coming up. Because, I guess I'll spoil it. You can have two reference values that point towards the same object value. And this is the part that confuses people. We can have a string S and a string T that both point towards the object value go. And that has very dangerous implications. And so for tracing tables, we might want to say that both S and T point towards the string value go. Instead of having to write S equals go and T equals go. We might want to say that S and T simply point towards go. Essentially, if you're using tracing tables, if you're using strings in tracing tables or natural numbers or any reference type, you will use an arrow instead of an equal sign. Okay, so now let's talk about assignment. Assignment in Java. I'm going to erase this. Does anybody want me to keep it up for a longer period of time? Okay, good. We're going to be talking about what Java does in the back end, behind the scenes, if you will, when you assign a variable, or when you do arithmetic operations on strings or integers. Basically, the difference between what happens behind the scenes in terms of reference types versus primitive types, and why is it important to this class. So the assignment operator copies the value of the expression on the right-hand side into the variable on the left-hand side. For primitive types, the value of can mean only one thing, which is the mathematical type that we're talking about. For reference types, it could mean the reference value of or the object value of. We don't know. What we're talking about here is the fact that when you say int x equals 4, what we're saying is that we want to assign the mathematical integer 4 into this variable x. Is what happens here. However, if we say string temp or t equals go, are we saying that we want to store the object value of go? Or are we saying that t, the object value or the reference variable, should be of type go? And then that should point to somewhere else. Could be either. Or you could make arguments for or against each one. All right. So consider the primitive type. We have an integer I equals k plus 7. First, the expression k plus 7 is evaluated. This is why I believe there was a question on the midterm as well. if you have something like 1 divided by 2, classic example, and then you try to store it in a double, the reason that it doesn't simply say, well, it's storing it in a double, why doesn't it just do the operation as a double, is because the expression is evaluated first. Everything to do with the expression is evaluated, and then it is assigned to the variable. So if everything is done on the expression side, then 1 divided by 2 is 0.5, truncates, integer, and that's what gets assigned to the double. So we always do the right-hand side first, and we express that value. So what is actually happening when we have int I equals k plus 7? Well, first we have to evaluate what k plus 7 even means. In this case, if k is 3, the expression evaluates to 10, and then the value 10 is copied into I. So the above statement has finished executing, and we have I equals 10. Hopefully this is not a groundbreaking subject. But what is actually happening in the back end of memory? Well, we begin with our primitive variable k, which is just the value of 3. Again, primitive type, so it's stored directly in memory. Then, in order to complete the expression, Java needs to store 7 somewhere. So we have what's known as a anonymous primitive variable. You don't have to worry about this, but essentially, Java says, in order to complete this expression, I need to have 7 stored somewhere. So I'm going to make this fake variable. It's called an anonymous primitive variable, just so that I can do the operation. And then it's going to say, okay, add those two together, store that in another anonymous primitive variable. In this case, we're calling it question mark b question mark. That's 10. And then finally, we're saying set that equal to a variable I. So, or next we're saying the declaration of int I says, hey, store something in I. What are we storing in I? Well, copy the resulting expression into that. And that's what it will happen. And then any of these anonymous primitive variables that we have will get cleaned up and tossed out by Java's garbage collector. What it's called. Oh wait, I shouldn't have deleted I. That's not what will happen. I will remain 10, but these anonymous primitive variables will be deleted and freed up for more space in memory. And we'll just be left with k equals to 3, I equals to 10. Again, hopefully not groundbreaking. This is what it looks like on the tracing table front. You have an integer k, and then you have an integer I. The anonymous primitive variables are not shown because they are an intermediate step in getting the result. Okay, that was not that interesting. So let's go through a more, I guess, interesting example. Considering the expression statement in this case, string s equals t plus io. And then if t is already stored as the reference variable pointing towards the object value OH, that's how we start. So this is what memory looks like at the beginning. So first thing that happens is we have another primitive, or we have another uninitialized reference variable, which we'll just call question mark. And that stores a reference to the string IO. And then, so we have the reference variable OH. We have an anonymous reference variable whose value is IO. And then we create a new uninitialized reference variable to store the result, concatenating the two together. That becomes IO. And then what happens is instead of the value being copied into, oh, well, this is the important part. Pay attention vigorously. The important part here is that instead of the value Ohio then being copied back into this reference location T, what we do is we simply say, hey, instead of pointing towards that value, you should instead point towards this value. The reference, or the reference value is instead set equal to the resulting object value Ohio. The resulting object value Ohio is not copied back into T. Right? As points. Oh, wait, no. I just lied to you. T still remains as OH. But this new initialized variable s, instead of the variable being copied into, we simply point towards this resulting value of Ohio. If we were thinking about strings as if they were primitive types, what we would think would happen is that we would have a new object value that would point towards the string Ohio. And this would be copied into that object value, but that's not what happens. Instead, the reference value simply points to where this uninitialized string has been set. And then Java's garbage collection will simply delete everything that we don't care about anymore. So this one here, and then T will remain as OH. We will have a new string S, which is Ohio. And then again, how it looks like on the tracing table, you have T, which points towards the value of OH, and then you have S, which points towards the value of Ohio, using the arrows instead of the equal sign, as we have learned. Okay, good so far? Questions, comments, concerns? Now, here's how it would look like using equal signs, which is wrong. Don't do this. It seems that the net effect of assignment is essentially the same whether we have primitive or reference variables, but that is not the case. You might be thinking, where does it get dangerous? This is where it gets dangerous, so lock in. Okay, consider I equals K. When we set two primitive variables equal to each other, say I is equal to, K is equal to 3. K is equal to 3, and then we're saying, hey, make a new variable I, which is the same value as 3. Since it is a primitive type, we copy by value. So we're saying, hey, look at K, whatever K is, just be that 3. And that's not too bad. Oh, I guess we're going to do it step by step. Okay, primitive variable K, uninitialized variable I, value gets copied into it. Note, now there are two independent copies of the variable 3. These are both in and of themselves variables which can be changed, modified, subtracted to, added to, multiplied to. They're independent, and this is what it looks like on the tracing table. However, comma. Now, we work with a reference type, string S equals T, where T is the value of OH. Reference type, object type, OH. What happens in this case, and where things get dangerous, is that instead of just copying the value directly into the object value, sorry, no, you're good. Instead of just, yeah, I know, it's very exciting stuff. Well, this is about to blow your mind. Instead of copying the object value into its own object value OH, in which case we have two copies of the string OH, instead, S simply points towards T's value of OH. So now these two variables, which contain the same string, point towards the same string, and not in the sense that they're duplicates of each other, in the fact that they are the same string. This is known as, terminology alert, aliasing. We say that strings S and T are aliased, or they are aliases of each other. Meaning that if you were to look at the reference location or the reference value of T and S, say where they're stored in memory, or where they point to in memory, say that this is reference location 22, they would both be 22. And that's dangerous for reasons we will get into. So string T goes OH, string S, uninitialized reference variable. Instead of just copying, it points directly to OH. These references are called aliases. And so how we write that on a tracing table is we say that S and T both point towards the object value OH. Very different than primitive types where the value is just copied. Okay, I'll let that sink in. I just blew all of your minds. Probably not good. Any questions? Awesome. Okay, the arrow notation helps us remember that there's only one object, but two references towards it. So we have two references towards the string value go. This is wrong. It is implying that there are two separate strings that both contain the value of OH, which is not true. Wrong. Okay, Here's why it's important. And this is the slide, I guess you could say. Aliases are dangerous because if you have a mutable reference type, say a natural number, where you might think that if you have z, wrong side of the chalk, which is a reference type, which points to 99, and then you say n equals z. Say we're thinking about natural numbers as if they were primitive types. Pretend with me for a second. 99 as well. And then we say n dot increment. Well, increment just takes the object value and increases it by 1. No harm, no foul, right? Wrong. All of you, wrong. Instead, the reference value points towards the same value. So when we call n dot increment, it is not only updating n, but it is updating its alias as well. 100. So you've subsequently accidentally just also incremented the value of z while trying to just increment the value of n, which is dangerous, very dangerous. This is not what happens. Try it step by step. Again, if you're thinking about it as a tracing table, you have z, which points towards 99, then n, which also points to 99. Now, calling n dot increment increments both of them at the same time, which is so scary and dangerous. This is why aliases are so, like, a good Halloween costume would be an alias. Be terrifying. Okay, questions on that? Yeah.
So say they like initialize the variable to like the same value, like 99 instead of putting z, would it still point to?
No. So you're saying instead of natural number n being equal to z, you said like natural number n equals new natural number 99. What happens is you have a separate variable. And in that case, it's okay. Right? Right. The only thing, because what happens is when you say reference type equals other reference type, what you're saying is, hey, point towards the same object value, which creates an alias. Yeah.
Does this happen for like strings too?
Yes.
Oh.
Which is scary. And it gets even crazier because if you pass in a natural number into, say, a static method, instead of doing pass by value, you're now doing pass by reference. So if you have a static method that takes in a natural number and all it does is increment it, and then you create a natural number outside of your static method and you pass it in, it's going to have that updated value after the method as well. So like integer, if you passed in, say, 99 into a static method that increased it, afterwards it would still be 99. So you're passing it by value. However, you pass a natural number, you're passing in the reference, increment it, it's going to be 100 afterwards. And that's like a big, it's like a big thing. So you'll get practice with it, but people still get confused. So this is what really happens. Both of them now equal 100 because they're alias to each other. Okay, an important claim here that we're going to make. The problem illustrated here that arises from the aliasing of references with natural number cannot happen with string or XML tree. Okay, I lied to you actually. It doesn't happen with string because since it's a built-in type, Java will take care of the aliasing for you. So if you like have two strings, z and n, and then you concatenate like a character onto one of them and they're aliased together, they'll still be different because Java will unpack the aliases for you.
So would it be like they're both pointing to the same string initially, and then would you like separate after? Or?
Yeah. So what'll happen, I think, like 64% sure here. You have string OH, and then you have string and OH, and then you say like n equals n plus IO. I think what happens is that it just makes a new variable reference.
Will there ever be like two reference like variable strings that point to two objects with the same object value?
Yes, you could do that. So like if you have string S equals Ohio, string T equals Ohio, like you're not setting the reference values equal to each other. So it'll be two separate things.
So then on like a tracing table, would you set them separately? Or?
Yeah. Mm-hmm. Okay. And same with natural number. If you said
we go back to this tracing table here, and instead of natural number n equals z, we said like natural number n equals new natural number 99. We would have two variables there. We would have z equal to 99, and then n also equal to 99, but a different 99. Right? And so how that would look on the tracing table is we have z points towards the object value 99, n points to the object value 99. What's different is that these have different reference types or different reference variables. Where they're stored in memory points to different locations. Say that they're next to each other. This is 23, this is 24. Where they're stored in memory, z would point towards 23, n would point towards 24. So while they're the same object value, their reference variables are different. Distinction between the two. Does that make sense? You can say no if it doesn't. Okay, good. Okay, this is what really happens. Okay, what's the difference? Immutable versus mutable types. Java reference types, again, as I said at the beginning, further divided into two different categories. Types for which no method might change the value of the receiver or any other arguments of that type are called immutable types. This is XML tree. This is simple writer, simple reader. You cannot change the value once it's initialized. And then mutable types, which are natural number, stacks, queues, which we'll get into, can be changed by instance methods. Yeah.
String would in like Word?
Yes. Because so strings are immutable, meaning that they cannot change. But you might be saying like, you can change a string. If I do s equals s plus IO, it's gonna change the value of the string. But how Java gets around this is it just creates an entirely new string.
Oh, okay.
So it's not changing the value of the string, but it's changing the value of the string. It's a farce. Okay. Categories of types: immutable, mutable, primitive. Primitive types are the nice easy ones. Okay, restated claim. You may reason about immutable types / variables as if they were primitives. So since the values cannot change, you don't have to worry about harmful aliasing. So you can treat them as if they were primitives. That's why you can treat a string as if it was a primitive. If and only if there are aliased references, you may not reason about mutable types / variables as if they were primitive. So if you have two reference types that are mutable, such as, all right, we're going back to these being natural numbers and then pointing towards the same thing. You can't simply reason about these as if they were primitive types. You can't assume that they're going to be pointing towards different values because they're aliased. The reasoning shortcut is unsound, may produce wrong results compared to executing the code. And then by wrong results, we mean this right here. Okay, just as the assignment operator copies reference values, parameter passing to method calls copies reference values. So this is what I was saying before, where if you have a static method or an instance method, which takes in a mutable reference type, actually, you know what, let's just draw a picture. It'll be easier to understand. Let's say that we have a static method called increment. I'm gonna leave out the method header just because it's not important. Natural number p, right? And the only thing that this does is it says t.increment. That's how you spell it. And then nothing else. Just calls t.increment. And then for comparison's sake, let's say we have an increment method which takes in an integer p and says t plus equals or t plus plus. Right? Here's how this plays out. Say you have a integer I, which is 99. Increment gets called, you pass in the value, it gets copied, 99. We increment it, t plus plus becomes 100. Method returns, no update happens to I, because we passed the value, not the reference. Uh-oh, it's reference time, right? Now we have, say, I, which is a reference type, points to the value of 99. Now, when we call increment on the natural number, what happens is this t just gets pointed towards the object value that was passed in. we're passing the, oh, actually, this is a wrong image. We pass the reference to I. So t points to I points to 99. Then when we call t dot increment, Java is going to follow the treasure map to I, follow the treasure map to 99. Okay, I'm finally at an object type. Let me increment. Okay, we're returning out of the method. I don't need t anymore. Let's get rid of that. But afterwards, I is now 100. So after the method call has run, any changes that you make to a mutable reference type that has been passed into the function remain. Let that sink in. That's the important part that people often get confused. All right, questions on that? Awesome. Okay, so if you have m.transfer from k, consult the contract from transfer from. I believe the reason that transfer from is so fast is because if we have a reference type m, which points towards the string, oh, sorry, the natural number 143, and then we have k, which points towards 70. I believe that transfer from is so fast. And the reason that it resets the value to 0 is that all we do is we say, hey, m, instead of pointing towards this value, point towards this value. And then k, go to 0. And that's way faster than actually digging through Java's memory to copy the values. So what happens after is that m will be aliased to an object value of 70, k will be referenced to an object value of 0. Okay, another reason or another way that this manifests is checking for equality. If you have ever tried to compare two strings using the equals equals method, sometimes you get bad results. And the reason for that is that the equals equals operator compares reference values, not object values. So this is not a problem for primitive types, ints, chars, doubles. This is a problem for reference types because if you have, say, m pointing towards 99, and then you have a k pointing towards 99, but this is stored at location 23, this is stored at location 24, and then you say m equals k. Well, what we're comparing is the reference values, not the object values. So it will return false. Okay. That's why we use the dot equals method, because the dot equals method compares object values instead. Okay. So here's an example. Oh, that's like the exact example that I used, except different variables. So m and k are two reference variables which alias to object values of 52. However, they are separate object values of 52. So if we say Boolean b equals m equals k, despite the fact that the object values are the same, it will return false. Now, say that they were alias to each other, they would return true because the reference values are true, or the reference values are equal in this case. And if you want to get around that, you can just use the dot equals method, which will always return the comparison of the object values in both cases. Okay, questions on that? Okay, I will give back the midterms now. All right, when I call your name, you can just come up and grab it. And then you're free to go if you have any questions. Eventually, I'll probably post a walkthrough of the exam so that you can look back, but that will be for another time. Okay.
Sorry.
No, you're good. I think the average was like an 81 something. Yeah. Okay. Agna,
Sure.
Pens code. Yeah. Melissa, Anya, Anurag, Arnav, Brandon, Brooklyn,
Hayden. Christian. Danny. Ethan. Farah. Ibrahim. Isaac. Sorry. Gene. Jessica. Jesse. Vincian. Jordan. Right, Logan. Mark. Maria. Maxwell. Cole. All right, Micah. Mutasi. Neil. Nemeg. Otis. Permay. Richard. Rohan. Sai. Steva. All right, Stephen. Temulin. Martha. Varun. Youngwon. Zoe. Did anybody not get their anything? Some general notes, the question about, whether or not the foo methods did the same thing tripped up a lot of people. And it was, they do not do the same because after the first if statement on the right side, the values will not be equal anymore, so that the second one will run. For the coding question, I love to comment, and if it says exit loop after found duplicates, that was a point that I took off just because after you found the duplicates, you should exit out of the loop, because if the array was a trillion billion elements long, and then the first two were consecutive duplicates, you don't want to go through the entirety of the rest of the array, because it would be an inefficiency. All right, and if you have any questions, you can message me / message me /